In this video, I want to talk about two additional perspectives on the sign of a permutation. So we've already really dug into this one about the sign telling you the parity of the number of transpositions that occur in your permutation as a product of transpositions. So I'm going to do these other two a little more quickly without all of the detail. So this one comes from Conrad's notes on the sign of a permutation. It's permutation matrices. And this is going to be something that gives an interesting example moving forward a little bit to the next chapter. Let's start by just writing down the standard basis vectors for Rn. So what is that? Like E1 is the column vector with a 1 in the first position and zeros everywhere else. E2 has a 1 in the second position and zeros everywhere else. En has a 1 in the nth position, zeros everywhere else. So given a permutation, we're going to define a linear transformation out of it, where T sigma of a linear combination of these standard basis vectors is going to take C1 E1 plus Cn En is going to go to Cn C1, but now instead of E1, we're going to get E sigma 1. What does sigma do to 1? Plus Cn times E sigma n. What does a permutation do to n? So what's the important thing here? T sigma sends Ei to E sigma I, and we're going to extend by linearity to all of Rn. So the idea is that you know what a linear transformation does to any element of Rn if you know what it does to any basis that you start with. So now, given a linear transformation, we can write it as a matrix. Like, what is the first column of the matrix is going to be what does our transformation do to our first standard basis vector E1? And then what does it do to E2? What does it do to E3? So here's an example. Let's say sigma is a permutation that takes 1 to 2, 2 to 3, 3 to 1 in S3. So T sigma takes E1 to E2 and E2 to E3 and E3 back to E1. So the matrix of this transformation is 0, 1, 0, 0, 0, 1, 1, 0, 0. The columns are what do you do to E1? What do you do to E2? What do you do to E3? One more example. Let's take the product of disjoint transpositions, 1, 2 times 3, 4 in S4. So this sends E1 to E2. It sends E2 back to E1. It sends E3 to E4 and E4 back to E3. So we get this matrix here. So what is true about the matrices that we get? If your permutation is Sn, in Sn, you get an n by n matrix, and you get exactly 1, 1 in each column in each row. So what's going on is you're permuting the standard basis vectors. So you're getting the columns of the identity matrix, but not written in the regular order, written in this order that is specified by sigma. So I'm going to pause and erase, and I'll tell you a little bit about this correspondence of permutation to linear transformation given by your permutation. Let's think about this correspondence where you start with a permutation sigma and you get a linear transformation T sigma. Or if you prefer, you could think about a matrix corresponding to T sigma. This correspondence is multiplicative. What does that mean? That the linear transformation T sigma 1 following T sigma 2 is the same as the linear transformation of T corresponding to the product sigma 1, sigma 2. Or if you think of everything in terms of matrices, you really get the matrix for T sigma 1 times the matrix for T sigma 2 is the matrix for sigma 1 times sigma 2. How do you see that this is true? Just check what each side does to the standard basis vectors. If they send the standard basis vectors to the same place, then they are the same linear transformation. Or if you think about it in terms of matrices, you also want to note that the multiplication of matrices is the composition of the corresponding linear transformations. OK, so what does that mean? Well, if you take the matrix corresponding to sigma 1, sigma 2, the determinant of T sigma 1, sigma 2 is the determinant of T sigma 1 times the determinant of T sigma 2. But like, what is the determinant corresponding to one of these matrices for these linear transformations? So what I'm going to say next, how much you get from it, depends on what interpretation of determinants you've seen before in your linear algebra class. But because these matrices have a single one in each row and each column, when you take the formula for the determinant as a sum over permutations, there's a single non-zero term. And if you haven't seen this formula, it's in Dummett and Foote as theorem 24 in section 11.4. But you can also just forget about this for now, and we'll come back to this kind of thing when we talk much more about linear algebra next quarter. But what this is going to tell us is that the determinant of T sigma is going to be the sign of sigma. So this gives us another way to understand why sign of a permutation is a homomorphism, because the determinant of the product of matrices is multiplicative. So that's sort of equivalent to saying that sign is a homomorphism. OK, so if you fix n and you take all of the matrices corresponding to permutations in Sn, what do you get? You get this set of n factorial n by n permutation matrices. And it's not just a set, because if you multiply two of these matrices, you get the matrix corresponding to their product. So what does this show? This shows that not only is this a set, but this is a subgroup of GLNR, and it's isomorphic to Sn. So inside this big infinite n by n invertible matrix group GLNR, we have all of these interesting finite groups, the symmetric groups, and then we can also find subgroups of these symmetric groups. And I'll say more about that in a few lectures when we talk about Cayley's theorem. So I'm going to pause and erase, and then I'll say one other perspective on the sign of a permutation, the one that is presented in section 3.5 of Dummett and Foote. I want to end this video by briefly saying something about section 3.5 in Dummett and Foote and their perspective on the sign of a permutation. So the setup goes through this special polynomial delta, which is a product over all pairs I less than j, where I and j are between 1 and n, of xi minus xj. So we have all of the xi minus something with a higher index, xj, where j is bigger than I. The idea here is that Sn acts on this polynomial. What does that mean? We apply sigma to this polynomial by permuting the variables. So everywhere that we see an x1, we're going to replace it with x sigma 1. Everywhere we see an x2, we replace it with x sigma 2. So now we get this product over all pairs I less than j between 1 and n of x sigma I minus x sigma j. So sort of form of the terms in the product hasn't really changed. We still have these binomials, x something minus x something else. And every term, xi minus xj, where I is less than j, appears in delta. What happens in sigma delta is we always have either xi minus xj, or we get xj minus xi. The idea is that something has to get sent to I, and something has to get sent to j. So at some point when we're going over all of these pairs, we have some pair where the pair includes xi and xj, but the order might be switched. We might have xj minus xi instead of xi minus xj. We can't get both because sigma is a permutation, and we also can't possibly get xi minus xi because this permutation is actually a bijection. We can't have two different variables getting sent to the same variable. OK, so what does that tell us? The absolute values of all the terms in here are all the terms in here. But we might have picked up a whole bunch of minus ones by switching the order a lot of times. So sigma delta is equal to either delta itself or minus 1 times delta. And the big question in this section is, which one is it? And Dummett and Foote define the sign of a permutation as the plus or minus 1 that you get by applying sigma to delta and seeing whether you get 1 times delta or minus 1 times delta. And then as a theorem, they show that this definition of sign is equal to the parity of, when you write sigma as a product of transpositions, the parity of the number of transpositions. So that's the idea. You can now go through section 3.5 of Dumb and Foot, and you can see whether you find that argument more or less clear than the argument that I presented at the beginning of this lecture. So I just want to close by saying that a polynomial like delta gets a special name. So if you have a polynomial in n variables, Sn acts on it by permuting these variables, x1 through xn. So if you have a polynomial f where you apply any one of these permutations and you get back f. So for all sigma in Sn, sigma f is equal to f is called a symmetric polynomial. And these show up all over the place in like algebraic aspects of combinatorics and algebraic geometry. For example, if you have 3 variables, you could have something like x1, x2 plus x2, x3 plus x1, x3. Any permutation you apply in S3, you're going to get back exactly this polynomial. OK, so those polynomials are really important. Delta is not one of those, because when we apply some permutations, we don't get back delta, we get back minus delta. So if you have sigma of f is equal to the sine of sigma times f for all sigma in Sn, then f is called an alternating polynomial. And what Dumb and Foot are showing here or defining here is that this polynomial delta is an alternating polynomial.